Good morning. My name is David Malin. This is Computer Science for Business Leaders, and we'll do some group introductions before long. But why don't we dive right in this morning to one of our first lessons, which is going to be on computational thinking. Indeed, today and tomorrow among the goals are to give you really kind of a top-down sense of what computer science itself is all about and computer engineering, particularly so that everyone in the room, even just after a couple of days' time, can hold their own all the more, so to speak, with engineers, can try to estimate perhaps a little more effectively how long projects might take or what might be involved, or at the end of the day, just what kinds of questions to actually ask so as to wrap your minds around technical projects. It looks like we have a mix of folks, though, and to give you a sense of who else is in the classroom on an aggregate scale, we'll give you a sense of some of the answers that you gave us to the Google form that we circulated in advance. But here's where we are today. So we're going to start off with computational thinking and talking about some fairly high-level concepts like abstraction and algorithms and representation, but we'll distill those into things much more concrete before long. After a short break, we'll then dive into internet technology. So how does the internet work? Most everyone here uses it every day. Most everyone here is on it right now. But what actually is underneath the hood, and what are some of the things that can go wrong, and why was it designed the way it was designed, and what are the kinds of questions to ask then when building a business on top of it? Indeed, after lunch, we'll focus specifically on a more modern incarnation of these technologies known as cloud computing. This in and of itself is mostly just a buzzword, frankly, but we'll distill exactly what that means and what some of the ingredients and building blocks are for using the cloud. And then this afternoon, after another break, we'll take a look at web development. We'll just scratch the surface, but it'll be an opportunity hands-on with laptops to get your hands dirty if you've never done it before, with a little bit of languages like HTML and CSS and the general Linux architecture, so that when you walk out today, we've tried to make things a little more concrete still based on the higher level discussions. Tomorrow, meanwhile, we'll start with a high-level discussion of issues of security and privacy and society more generally. Things like a few months back, Apple created a bit of a stir with its butting heads with the FBI, as you may recall, as they tried to get into someone's iPhone. We'll talk about that, what it means for encryption and what that technology actually is. Looking again at another industry topic like Dropbox, or sharing of files, which at first glance might seem like a wonderful service and exists from Microsoft and Google and any number of other forms. But what does it actually mean to be storing your files on services like Dropbox for your own privacy and security? Then we'll talk about programming, so what it actually means to write software, what some of the basic building blocks are, followed by technology stack, so a general way of describing like what are the sort of ingredients that you can bring to bear when trying to build a business or a website or a mobile application. What's the sort of alphabet soup these days? And then lastly, web programming, looking not just on the aesthetics of web pages using languages like HTML and CSS, but actual web programming using languages like JavaScript or others. And we'll talk about some of the related technologies there. So here's who's in the room. When asked via that Google form, how would you describe your comfort with technology? It's split between very and somewhat, with a few of you saying not very. So this is a nice mix, and certainly feel free to ask any and all questions as we proceed today and tomorrow. And we'll see, perhaps based on questions from me to you, just how very is, perhaps, but we'll get there. And then when asked as well, do you have any programming experience in any language? This was a bit more of a mix, with 35% of folks saying no prior programming experience, some of you saying some, and then just a few of you saying a lot, which is a good mix too, because hopefully then when we do the hands-on portion, there'll be a little something new for everyone. So if you'd like to follow along today or tomorrow, all of these slides, including any edits we might make in real time, is at this URL here. So if there's one URL you want to keep open today, let me pause for just a moment and suggest you go to this bit.ly URL, CS for Business Leaders 2016-07. I'll linger for just a moment on that. In the meantime, let me get these out of the way. Just let me know if you have any trouble viewing those. All right. Typing seems to be slowing, so we are, if you don't have it yet, just look at the person next to you if you could. So we're now at computational thinking. All right, so what does this actually mean? This is kind of one of the buzzwords within academia for describing one of the returns that you get from studies in computer science, what you get out of it, what you learn how to do. And indeed, many fields teach you how to think, or so they claim in course catalogs, descriptions, and so forth. But computational thinking is actually a sort of ingredient that we can leverage. It's a way of thinking more algorithmically, so to speak, more methodically, and bringing to bear to problems sort of a more organized way of thought. But to get there, let me propose that there's three ingredients to this notion of computational thinking. Specifically, let me propose that computational thinking can be distilled as input going into something called an algorithm, going into something, or producing rather, outputs. So in other words, computational thinking is all about building this process, this pipeline. But this invites the question, well, what do we mean by inputs and what do we mean by outputs? Well, inputs are just whatever the problem is that we have to solve. In a little bit, we'll play around with an old school technology, this phone book. This might be the input to a problem. Look someone up in this phone book. So here is the physical input, and the additional ingredient, the additional input is someone's name, whom you might want to look up. And the output, hopefully, is going to be from that problem, what? Intuitively. If the input is a phone number. So hopefully that's going to be the output. Meanwhile, the algorithm is the process that my hands engage in order to find someone's name in this phone book and in turn their number. So that would be the algorithm or the problem-solving steps in between the inputs and the outputs. But how does a computer and how do we humans represent inputs and outputs? Well, at the end of the day, most everyone here probably knows that computers only understand what? Alphabet, so to speak. Binary, so zeros and ones. And even those of you who said you were only somewhat or not very comfortable probably at least know or have heard that computers indeed only understand zeros and ones, the so-called binary system, bi meaning two, and that's two because you only have 0 and 1 in your vocabulary. We humans, by contrast, tend to use the decimal system, dec meaning 10, so we get to speak in terms of 0 through 9, not to mention alphabetical letters and more. So if computers only have zeros and ones, though, how could we possibly go about representing the number 2 and the number 3 and the number 4, let alone A, B, and C, let alone images and movies and audio files and any number of other formats that we just take for granted these days? Well, think back to grade school, perhaps, when you first learned that this pattern of symbols, 1, 2, 3, represents what number in decimal? 123. Excellent. So that all comes to us very intuitively, certainly these days. But why is that? You might not have thought about it for some time. But if you're like me, you probably learned back in the day that this 3 is in the ones place, or the ones column, and the 2 is in the tens place. All right, so the tens place, and then the hundreds place, thousands place, 10,000s place, and so forth. But why is that significant? Well, 1, 2, 3 is just a pattern of symbols. That's our vocabulary, 0 through 9. So the fact that we've ascribed meaning to the places in which these digits are means that we can do 100 times 1 is meant to be the arithmetic, and then that's plus 10 times 2, and that's plus 1 times 3. So this, of course, is 100 plus 20 plus 3, which gives us 123. Now, at the end of the day, we've still written down the exact same thing, but we've gone from just a pattern of symbols, 1, 2, 3, to a higher level notion of a number, a decimal number that we know now intuitively is 123. Well, how many of you, just to get a litmus test of before and after, how many of you know binary or could recite numbers in binary? OK, good. Otherwise, this is going to be very underwhelming. So it turns out all of you, I claim, a bit boldly, already know binary, or certainly could make this leap within seconds. So instead of having 1s, 2s, 3s, and 0s, and 4s, and 5s, and 6s, 7s, 8s, 9s in our vocabulary, now we're limiting ourselves to just 0s and 1s. And so if we have, say, 3 digits, just for the sake of discussion, we also now, if we only have 0s and 1s, are going to want to change these placeholders. Because before, 1, 10, 100, 1,000, those were powers of 10. And that was significant because we had 10 digits. So just intuitively, or take a guess, what are the powers going to need to be if you only have 2 digits at your disposal? So powers of 2. So we still start with a 1s column, which is 2 to the 0. But then we have 2 to the 1, which is the 2s column, 2 to the 2, which is the 4s column, 2 to the 3, which is going to be 8, 16, 32, 64. And so the columns are still powers of some value, but in this case it's powers of 2 instead of 10. So based on that logic, if I told you a computer was storing this pattern of bits or binary digits, what number is the computer thinking of in decimal? So just 0, right? If the logic is the same, 4 times 0 plus 2 times 0 plus 1 times 0 gives us the higher level notion of 0. So this is how a computer would store the number 0. So even if you've never spoken or thought about binary before, how do we represent, say, the number 1 in binary? Yeah, so 0, 0, 1. And of course, to represent the number 2, we're going to do what? This. Yeah, so trick question. So this would be 3, just based on the process we've been using before. So that's not correct. This would be the number 2. This now would intentionally be the number 3. The number 4, of course, would be 1, 0, 0. And then we can count up further. But actually, let's count up as high as we can. With 3 binary digits, aka bits, what's the largest number we can count to? Yeah, 7, right? And you know this because if you only have zeros and ones, and we already know that putting zeros everywhere gives us 0, clearly the largest number has got to be 1, 1, 1. So that's 4 plus 2 plus 1 is 7. But how then does a computer count as high as 8? Yeah, so we need more powers. We need more bits. So just like you might carry into the next place using the decimal system or grade school arithmetic, same idea here. If we want to now count as high as 8, that's fine, but we're going to need another bit in the so-called 8th place so that we can represent this. Now, as an aside, how many bits does a computer typically use to store numbers? Does anyone know? It's bigger than 4, otherwise we wouldn't have much to do in a computer. 16 used to be 16. Nowadays it's a little bigger. 32 is very common and very much in vogue these days is 64. So even if you've never really thought about what it means, if you've heard the expression 32-bit or 64-bit, it's usually in the context of CPUs or computers or operating systems, well, that signifies essentially, how many bits does that computer use to store numbers? Specifically, it means how many bits does it use to store addresses of memory, but more on memory in just a little bit. But that's to say, if a computer has a 1's place, a 2's place, a 4's place, 8, 16, 32, 32 total such bits, the largest value a computer can represent is 2 to the 32. And so if there's one number, roughly, you take away from today, let's consider this one. How high can a computer count? If a computer can highest count as 2 to the 32. We could do this. So 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128, 256, 512, 1024, 2048. It's going to get hard soon, so save me. So it's going to be a pretty big number. It turns out this is roughly 4 billion. Roughly 4 billion. Now, for those of you who might have grown up with PCs and might have built them or bought them certainly yourself, you might have at some point realized or been told that your computer only stores, or rather, your computer can only support up to 2 gigabytes of RAM. Did anyone ever run into this limitation? So if you ever ran into an upper bound on how much memory your computer could support, sometimes it's just because the manufacturer has some hard-coded limitation. Apple does this just for money and financial reasons or engineering reasons. But back in the day, especially with PCs that you could upgrade, there was still an upper bound on how much RAM you could put in a computer. You could only, in many machines, put in 2 gigabytes because at the time they were using 32-bit values, and actually 31 bits because they were stealing one of them to represent negative signs, but more on that perhaps another time. So that meant not 4 billion, but 2 billion. And if you've got memory in your computer, and we'll talk more about memory in a bit, if you've got memory in your computer, but you can physically only count as high as 2 billion, you better have no more than 2 billion bytes of memory, because everything at 2 billion and 1 or beyond, essentially, would just be inaccessible. You wouldn't have the vocabulary with which to express it. Nowadays, this is less of an issue, and computers these days are doing 64-bit values to the 64. And this is not a number I can pronounce, but I can bring up a calculator. If you've ever wondered what 2 to the 32 is, that, of course, is 4 billion. which looks like that. And just to give you a sense of the size of 2 to the 64, that's a lot more bytes. That's way more RAM than we would ever be able to afford or fit physically, probably in a computer, at least right now. So why is all of this important? Well, we only seem to have at the moment a conceptual way of thinking about what goes on inside of a computer. We're just doing things with markers and with numbers on the screen. But at the end of the day, the computer is a physical device, and a phone, which is essentially a computer, is a physical device. So what's going on underneath the hood? How do we get from these abstract ideas of like counting to 7 or 4 billion to actually doing that physically in a computer? Well, what's one of the only inputs into my computer at the end of the day is this thing here, the power cord. And even if you're not an electrical engineer, what comes out of the power cord? So electricity, right, comes out of the holes in the wall. We can keep things very real today. And you probably remember generally that there's electrons involved, right? Little electricity is flowing in one direction or another. And that suffices for today's purposes, certainly, to know that electricity is an input. And you know that certainly that when you have electricity, you can turn things on. So if I want to turn on this light on my phone, you can think of that as it consuming some electricity. Electricity is now flowing through the device because I've turned the switch on. And now when I hit it again, it's off. So it turns out computers do fundamentally work in quite the same way. If you think of your computer as having a whole bunch of little switches, or light bulbs, if you will, inside, if those are on, you can think of the computer as representing a 1. And if they're off, you can think of the computer as representing a 0. So my phone right now is in the off state, so to speak. And now, once I turn the switch on, it's in the on state. So I might say that my phone is currently representing a 0. And now it's representing a 1, 0, 1, and so on. But unfortunately, with just one switch, one light bulb, I can only count so high. And it's around this time I like to borrow one phone. Can I, a phone, that one I can turn on. May I? I don't need to unlock it. I just need to turn the flashlight on. So everything is safe still. So if now I have 2 phones at my disposal, you can think of this one as being in the 1's place, this one as being in the 2's place. So quite trivially, what number am I representing right now? Both are off. Right, so they're both off. And if I go ahead and turn on this one, I'm now representing 1, because this is the 1's place, this is the 2's place. Now if I turn this one on, I'm representing 3, because 1 and 1. And if I turn off this one, I'm representing, of course, 2. Now with 2 phones, I can only count as high as 3, 0, 1, 2, 3, because that's how many ways I can permute the on-off switches. Now certainly, thank you, a typical laptop has many more than just 2 switches. It might have, turn this off, it might have thousands of switches, or millions of switches, or tens of millions of switches these days. And indeed, if you've ever heard the expression transistor, back in the day, a transistor radio inside of a computer, a transistor is really just a tiny little switch that if it's on, allows a little bit of electricity to flow and get stored perhaps, and so that gives us a 1. And if the switch is off, that gives us a 0. So inside physically a computer, there might be millions or tens of millions of these switches, and that's how we can store so much darn information, and compute so much information all at once. Unfortunately, there's a downside of using electricity and switches in this way. And I deliberately turned my flashlight off a moment ago because I was probably worried that what might happen? The battery might die. So if the battery dies, or if in the case of my laptop, my battery dies and this power cord comes off, presumably all those little light bulbs, all those little transistors naturally switch off, which is not good for your Excel files and your Word documents and anything else that you might be storing locally on your computer. So what do computers instead use to store data persistently or long term? Yeah, so memory, and it turns out there's different types of memory. Let's distill this for just a moment. So there's different types of memory. We've been talking about bits, of course, which might be turned to zeros, which might be represented physically with little transistors turning on and off. And so this takes different forms, but let's go ahead and describe a few types of memory. One, there's little things called registers. These are typically 32 or 64 bits of memory inside of a computer's CPU. And we humans really never should care about how many registers a computer has. It's not a selling point of a computer per se. It's a very low-level implementation detail. But it's about the smallest unit of measure that a computer or its CPU, central processing unit, might actually care about. There's then stuff called RAM, which is what all of us are intuitively describing most likely as memory, random access memory. This is the stuff that does get lost when you lose power or when your battery dies. It's for non-persistent data, and RAM is where programs live when you're using them or when files are open. So if you double-click Microsoft Word or some such program on your desktop and a window opens up, essentially what's happened is that program, Microsoft Word, has been copied from somewhere permanently on your computer into somewhere temporary on your computer called RAM. Why that is, we'll see in just a moment. And where it came from was probably something called a hard drive. Now, back in the day, these might be called HDDs, hard disk drive. The catch is they're not really hard disks anymore. They're not spinning platters, as we'll soon see. They're also called SSDs now for solid state drives, which means they're purely electronic, but they store their charges even after you lose power. But this is kind of the pipeline from one to the other. And it turns out we could do this all day. There's something called L1 cache in here, level 1. There's L2 cache in here. Those two are very low-level details. But this is just to say, when we humans say memory, frankly, we could technically mean a whole bunch of different things. But odds are humans mean this one here. But it's different from this kind of memory, your hard drive, because this is where your data is stored permanently. So when you install Microsoft Word or Excel or create a file and go to File Save, all of those zeros and ones are somehow stored here. But when you double click on the program or open the file, they're temporarily copied in duplicate, essentially here, while you're using them. Now, why might there be this duality? If you put on your so-called engineering hat, why would we have so many different types of memory? Because as an aside, the stuff that's in here eventually ends up in here, and a little bit in here, and even less of it, but some of it in here. So like all of these steps, moving things around. Why would we have this pipeline from long-term to super short-term, would you think intuitively? Speed, what do you mean? Yeah, so less material. So in speed, though, in what sense? Like, is one of these slower or faster, would you conjecture? Oh, so the RAM is smaller. So that's indeed the case. A computer might have 2 gigabytes of RAM these days, 8 gigabytes of RAM, but low numbers of gigabytes, whereas a hard disk might have 512 gigabytes or 1,024 gigabytes, aka a terabyte, or even more than that. But why, this seems silly, like why have less of this if this is the good stuff, right? This is where your programs and files are living when you actually care to use them.
Because one is just the working memory and the other is the stored memory?
So true, one is working memory, one is stored memory, but why not just use your hard drive for working memory? Like why complicate things? You don't want to lose, but if I'm storing everything always on my hard drive, it would stand to reason that I'll never lose it. Whereas if I load something into RAM while temporarily working on it, power goes out, that's when all of us start to swear because that's when you've lost data potentially.
I guess he was saying like speed and the amount of space you put in.
Speed, and yeah, and let me fill in a blank here. It's indeed the case that this is bigger, this is smaller. This is bits, this is maybe terabytes. But this is also super fast, and this is, relatively speaking, super slow. So there is this trade-off between size and space. You want a huge amount of space, ideally, for all of your personal files and work files and so forth, so you don't have to run out of space and delete things and just generally do that kind of dance. But this space, as a result of being cheap, tends to be pretty slow. And as a result of being mechanical, as we'll see in a moment, also tends to be slow. Back in the day, this was a physical device with a moving platter, not unlike record players of yesteryear, that is just subject to laws of motion and physical speed limitations. Whereas this is purely electronic. And even RAM is purely electronic and therefore much faster. So if you have more of this and less of this, but this is slower and this is faster, why not just have more of the fast stuff? So just to be clear, this is more, less, fast, slow. So why not just have more fast somewhere in the middle, like more RAM? It doesn't necessarily take more electricity, but good thought. Yeah, it's really this issue right here. It just happens to be the case still that the higher you go up on here, certainly versus RAM versus hard disk space, this is just a lot more expensive than hard disk space. So yeah, you could have a terabyte of RAM, but you're really going to pay for it. And no one really supports systems that use that because for some of the intuition that some of you had where this is really just working memory, I don't need to run all of my programs at once. I might run one, maybe half a dozen if I have multiple windows going, but it's a subset most likely of all of the stuff I've installed over time. I'm not going to have every Word document open that I've ever created. I'm probably just going to have one or a few. So working memory can be logistically just smaller. And so even though it's more expensive, we can tolerate that because we don't need as much. And so these are some of the trade-offs. And when you're buying a consumer PC or Mac, frankly, the only ones you really have choice over, discretion over perhaps, are those two. And more RAM tends to mean more expensive. But why might you want to have more RAM according to this logic here? Why might you want to spend a few $100s more to get the nicer Mac or the nicer PC with more RAM if everything else is constant? Faster, why? That's correct. But why does more RAM make your computer faster? Bigger working memory.
Pull more things from your hard drive at a given time and use them all at the same time.
Yeah, that's what it boils down to, but there's a reason that it actually feels to the human faster. It turns out that even if you only have like a gigabyte of RAM, you can actually cram more than a gigabyte of files and programs into RAM, which seems a little counterintuitive. But that's because of a technology called virtual memory. And computers have had this for 20, 30 years now in some form. Back in the day, you used to have to pay for and install special software to add virtual memory to your computer. It was a feature. Nowadays, it just comes with Windows and Mac OS and Linux and Unix and other operating systems. But virtual memory is a feature of modern operating systems that creates the illusion that even if you might have physically 1 gig of RAM, the computer will let you think you have 2 gigabytes of RAM. But the moment you try to add the billionth plus 1 byte to your RAM, what the computer does is it does a little switcheroo. It looks at your RAM, realizes, oh, yes, Excel is running, but you haven't touched that spreadsheet for a minute or for an hour or for a week. I'm going to secretly move Excel from RAM back to your hard drive in some temporary scratched locations, or some temporary space that you don't even have to know or care about, so that you can load that additional file that you just double-clicked on and go about your business. So what happens, though, if I just say, ooh, wait a minute, now I do want to play with that Excel file. So I click the little icon in my toolbar or whatnot for the Excel program. That then gets foregrounded. And if you've ever seen this happen visually, sometimes computers have this, like, it kind of feels painfully slow as the window is going from the background or minimized state to foreground. Like, why is that so slow? What might be happening? Yeah, go ahead. Oh, okay. From?
Well, I'm just saying it's retrieving it from the hard drive, so it's taking it from deeper memory.
Exactly. Remember that this is slower, this is faster. And so if Excel was secretly swapped out by your operating system so that you could use that memory for something else, the moment you want Excel back, your computer has to secretly move it back from the hard drive to RAM. And that's what creates that feeling of slowness. So it's not so much that just adding RAM to a computer makes your computer faster, because if you're only using a few programs or files at any one time, you could have an infinite amount of memory. If you're not going to use it, it's not going to have any impact on your computer. But if you have relatively little RAM, but you've been using your computer and programs and files so much that you're constantly swapping, so to speak, unbeknownst to you, but underneath the hood, between RAM and hard disk again and again because of virtual memory, then yes, more RAM will help. So as in a consumer perspective, frankly, just spending on RAM tends to be a good thing. There tends to be an upper bound realistically anyway, because this way you don't have to think about these kinds of things as well. But that's a slippery slope. Of course, paying for more hard disk space is great too, because you never have to worry about deleting things. Paying for a faster CPU, central processing unit, will just make everything faster because the computer can think faster. So even though I say more is better, it all, of course, has this impact. But this is the first such example of a trend we'll see today and tomorrow of these trade-offs. And in retrospect, it might seem pretty obvious. So better is more expensive, faster is probably more expensive, but I can get less of it to sort of balance my budget. This notion of trade-offs is going to be constant throughout computer science. In this case, it might be something like speed and cost or speed and quantity, but we're going to see other such trade-offs as well. And that really, at the end of the day, is what's interesting about or hard about engineering, is having to make those educated decisions as to which one is more important and when. So let's now scale up from something conceptual to something physical but small like a phone and a flashlight to actual hardware, something like a hard drive with which some of you might be familiar from yesteryear. Most of your laptops today probably have what are called SSDs, solid state drives. But if your computer has a fan or if you've ever heard clicking, which is generally not good, that's because you have a hard disk that works a little something like this. Let me go ahead and hit play.
The hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These in turn control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet it all works at terrific speeds.
So now let's zoom in a little lower level on where the bits actually are on a physical device like that in version 2.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
Okay, so this is all to say that not only do we have a conceptual mental model for how to count higher than 0 and 1 to 2 to 3 to 4, we also have a physical way now of representing these zeros and ones, not only temporarily in stuff like RAM and inside of your computer by way of transistors, turning things on and off, but also permanently. So to be clear, if I am often reminded when we talk about hard disks and storage of this guy from many years ago, although maybe he still exists. So Wooly Willy. So if you remember this little toy, it's just a plastic container below which is a face, and then there's all these little black magnetic particles, and you get a little red stick that itself has a magnet on it, and you can draw mustaches and hair and so forth on his face. But those little magnetic particles are essentially a much larger analog of this thing here. So as the video discusses having these zeros and ones represented by these little blue and red ovals, that's like saying if the particle is oriented like this, it might represent a 1. And if it instead is this way, south-north instead of north-south, it might represent a 0. So if you ever years ago remember floppy disks and you ever moved that little metal sheath over the floppy disk and touched it, there was indeed a floppy disk inside. But what you're touching is a platter not unlike this that had a lot of magnetic particles that unfortunately you just moved or destroyed or corrupted essentially by touching them. And that's why there was that metal sheath on top of it. All right, so if we can store permanently or temporarily zeros and ones, that's all fine and good. But it seems that all computers are good for is computing things like numbers or calculating, really. How do we get from zeros and ones and twos and threes and just numbers more generally, 4 billion, maybe that high, to things like letters so that we can actually implement Microsoft Word and email? And how do we then get higher still to things like images and movies? Well, let's start with the first. If all you have is zeros and ones in your alphabet, how could you send messages textually to someone else? If we have just zeros and ones, yeah.
Maybe like the A would be 1 and B would be 2 and then C would be 3.
Yeah. OK, well, what do people think about that? A is 1, B is 2, C is 3, and so forth. Like it? Yes? No? It's kind of arbitrary, but it's clean, it's nice, and so long as all of us humans agree, it's actually perfectly correct. Now, it turns out the world didn't quite standardize on 1, 2, 3 for ABC. They started counting a little higher just because of punctuation and other symbols on the keyboard. But indeed, that's exactly the case. It turns out that the world decided some time ago that if a computer is to store the capital letter A for the purposes of a document or an email or whatnot, it's actually going to represent that A using the decimal number 65, or more specifically, whatever pattern of bits represents the number 65. And let me try to figure this out. So if I have the 1's place, the 2's place, the 4's, the 8's, 16's, 32's, 64's. So in this case, I need 1, 2, 3, 4, 5, 6, 7. And indeed, it turns out that 7 is going to be significant in a moment. How do I represent the number 65 using binary? I need 7 bits, 7 zeros and 1s, but what pattern? Yeah, so thankfully this one's actually a little easy because you just need a 1 at both ends. You need a 64 and you need a 1. So that gives us 65, which is to say, if you're writing a Word document or you're writing an email, at the end of the day, what you're really doing when you hit the capital letter A on your keyboard is telling the computer, store the decimal number 65. But what does that mean? It can't store 65, but it can store zeros and 1s. So you're really telling the computer when you hit the capital letter A, give me 7 bits, permute them to look like this, and store those bits somewhere in the computer's memory. And indeed, it turns out that the capital letter B, by convention, is 66. C is 67. ... Lowercase a is 97. Lowercase b is 98. And there's a couple of hundred more because of all the various symbols on the keyboard. And at the end of the day, this is a system called 7-bit ASCII, which is just a fancy way of saying American Standard Code for Information Interchange, which is not something you need to remember, but it's a slightly more refined system than just the obvious A is 1, B is 2, C is 3. They also took into account punctuation and other symbols as well. Now, it turns out that 7 bits isn't all that much. Not to dwell too much on math today, but how high can you count if you only have 7 bits? What's the largest number you can reach? It's 128. Why is that? Well, if you have 2 possible values here, 2 possible values here, 2 possible values here, it's 2 times 2 times 2 times 2, which is 2 to the 7th, which does equal 128. That's all fine and good for like American English, because we've got like A through Z, so that's 26, but then lowercase and uppercase, so that's 52. I like exclamation points, so that's 53. There's space bar, 54. There's bunches of others, but certainly in other languages, especially certain Asian languages where there's a whole symbology, 128 total possible characters isn't going to cut it. So this was very American-centric, American Standard Code for Information Interchange. So nowadays, not only is it more common to use certainly 8-bit for extended ASCII, but actually 16-bit values called Unicode. And Unicode is just a smarter system that actually accommodates the fact that not everyone in the world only needs 7 bits. We sometimes need more to represent certain symbols. And I guess probably last math exercise, what's 2 to the 16? How many characters can we handle now? How many keys on a keyboard, so to speak? Is bigger. 65,536. I know that only because I asked that rhetorical question so often. All right, so that's a lot, and that's decent certainly to represent textual characters. So at the end of the day, what's the key ingredient? Well, we just had to decide on a system. We just had to decide somewhat arbitrarily, but globally consistently, 65 shall represent capital A, 66 shall represent capital B, and it's this mapping, this code that we all just need to agree upon. But then how does a computer know when a number, how does a computer know when a pattern of bits, zeros and ones, represents A or 65? How might we address this? Yeah, Avi?
There's one switch that changes the mode.
Yeah, one switch that changes the mode. Not bad, not bad. Unfortunately, the catch there is this. We're only, at the moment, narrowly talking about numbers and letters, but what about images and movies and any number of other file formats? That seems a slippery slope if we have a way of encoding the type of program, because there could be an infinite type of files that people create over time. So the storage space is just going to grow and grow and grow. So not bad, but it's probably going to run into problems as soon as we want to do more than just numbers and letters. what might you do instead? I'm sorry? So have another code for 65. So not bad, but at the end of the day, that code is going to have to be a pattern of bits. So we could absolutely come up with some other pattern of bits. But the problem is there's an infinite number of numbers in the world. Right? We can count up past 4 billion as humans to 8 billion to 16 billion to a trillion. And unless we decide no one can ever use the following numbers in like a math program, you can't really reserve any patterns of bits for your A's and your B's and your C's. So we need them both to coexist somehow, where sometimes this represents 65, but other times it represents A. Yeah, Grace? Yeah, why don't we kick it to the program to decide? So it's not bad intuition to kind of try to embed the information in the data itself, but it's easier and dare say more scalable to just leave it to the program that you're using to decide, am I looking at numbers or am I looking at letters? And to oversimplify, Microsoft Word, when it sees a pattern of bits, presumably is going to interpret that pattern of bits as letter, 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 because together that gives you a whole essay or document or whatnot. Meanwhile, Excel might view that same pattern of bits as numbers, but of course Excel can handle other things. An email program might view it as letters. A calculator program might view it as numbers. But of course, those programs could use different patterns for different types of data, numbers and letters. So it all is context dependent. And so Grace is spot on. It really just depends on the program. It is up to the program to decide whether it's looking at numbers or letters. Yeah?
Something to do with the terminology strings, binary, and so on that we found in programming language?
It does, yeah, absolutely. In fact, we'll see a little bit of this tomorrow when we talk about programming specifically. A lot of programming languages actually put the burden on the programmer, the author of the software, to decide in advance, do you want to represent a character or a number with the following sequence of bits? And these are called data types in programming languages. So it turns out we leave it to the program, and it just has to decide how it's going to interpret these patterns of bits. All right, so if that's the case, we now have this scheme for encoding letters and numbers. What about colors? Let's kind of step things up a notch. How could we represent colors? Yeah, Sarah?
Similar, a string of numbers, like the, what is it, hexagonal code or whatever?
Yep, hexadecimal.
Hexadecimal code.
Yep, so we do have systems like that, and in fact, we'll see this actually in HTML later today. You can see this in Photoshop actually. And in fact, I don't know if I'm going to be able to launch Photoshop on here in this account. Let me see. I'll accept that. Oh, we got away with it. All right. This guest account. No, damn it. Wait, let's see if we can use it anyway. OK, we can. All right, so this feature is free. So notice here, I have the ability to type in this number down here. I'm going to go ahead and type in 000000, and notice what color I get is black. And this is actually equivalent to this here, 000. And these letters you might recall from yesteryear. RGB, it's an old school expression, but still has meaning. What's RGB? Red, green, blue. So it turns out that you can make any color of the rainbow by just mixing in some red, some green, and blue, so different wavelengths of light. So let me go ahead and try that. Let me give a little bit, and notice right now we're at black because I have 0 of each of those, so the absence of any of those colors shall be black. And now let me give myself a little bit of red. That didn't really change things. And actually, let me change this to black so we can actually see a difference here. OK, so new and current. So let's give a little red. Definitely don't notice the difference on this projector. How about 10 of red? No, how about 100 of red? OK, so once we ramp it up to 100, that's a good amount of red. Let me try 200. Oh, that's really red. And now 255, really red. How about 1,000? That's a bug, because you can only count as high as 255. So here we're already seeing issues of representation. Photoshop, to represent the amount of red in a program, is using how many bits, apparently? 8, yeah. So I keep asking numbers, but I think I'm only asking the same 3 numbers all the time, or maybe same 4 numbers. 128, 256, 65,536, or 4 billion shall be the answer to any math question today. So 8 bits is sufficient, because 2 to the 8 is 256. So indeed, it looks like Photoshop, to represent the amount of red in the program is using 8 bits, where apparently 0 means no red, and 255 means a lot of red. So let me try that. 255 gives me, indeed, what looks like a lot of red. Now, if I change that back to 0, how about a lot of green? You see, that's how we can represent green. And if we get away from that and do 255, we might represent a lot of blue in this way. And now we can really start to have fun. If we do a lot of red, a lot of green, and blue, we get white, as though you're combining all those different wavelengths of light. How about like an even mix of 100, 100, 100? That's apparently how you represent gray. Anyone want to request a value? There's not much intellectual upside of this, but we'll just try one more color. 50. So give me 50 red, 50 green, 50 blue, still gray. Even quantities seems to give us gray. So how about we ramp this up to 250? That's an even still red. How about 100? Oh, there's orange, 150. So that's how you make orange, by mixing in that. And what if we ramp this up? Now it's a little more peach-like on my screen at least. That's how you get pink. And we could do this all day long and really not get anything out of it. So what's the real takeaway here? RGB is really telling us how much red do you want, how much green, how much blue. Each of these is 8-bit values. So we have a number and a number and a number, and combining those numbers, 8 plus 8 plus 8 bits, gives me what I would generally call 42-bit color. So if you've ever seen that, maybe even in your Mac or PC, if you ever futz around your display control panel or the equivalent, sometimes you'll see, do you want thousands of colors, millions of colors, or even bigger numbers still? That's just the user-friendly way of saying, do you want 16-bit color, whereby you're using only 16 bits to represent the color of a dot on a screen? Do you want 24-bit color, which means do you want to use 24 bits to represent the color of each dot, or perhaps even more still? Back in the day, when some of you first got computers, how many bit color was there? 16 was actually pretty good. Games were starting to look pretty nice in 16-bit color. Windows 3.1 was probably 16-bit color, or 8, no, it's probably 8-bit color. So 8-bit back in the day, but some of you surely had older computers still. Even I, my first games were, 2 colors, for which you only need 1 bit. And it wasn't even black and white. It was probably like black and green, where green was white. And so that was monochrome, which is really just a fancy way of saying 1-bit color. Or maybe this is the fancy way of saying monochrome. So what's the takeaway here? We can represent colors simply by using numbers. For instance, 0 to 255, where 0 means very little of this, 255 means a lot of this. And so long as we humans standardize the world of colors also, as we did for letters with something like RGB, how much red, how much green, how much blue do you want? We can mix those together. And now in the context of graphical programs or maybe web browsers, we can say, oh, this pattern of 24 bits is meant to be represented as the color of a dot on a screen. I shall interpret it as such and not as a number or as a really big letter or as a sequence of 3 letters. So this gives us the ability to represent the color of one dot, one so-called pixel on your screen. And pixels are so small you can't really see them. But if we went up to like the TV on the screen here, or if you have an older school TV at home, if you go up close to it, you can probably see tiny little dots, essentially pixels. That's not an image. That's just a dot. So what then is an image? How does a computer represent images? A sequence of pixels, right? An image, at the end of the day, especially like old school comic books, is really just a sequence of pixels, like something like this, whereby this is a 4 by 4 grid of pixels. And so long as I allocate 24 bits for this color, 24 bits for this color, 24 bits for this color, and so forth, I can represent a graphic. And in fact, let me see if I can find one real fast. Actually, let's see if we can make one real fast. So if I draw a grid like this, let's see if I can allocate enough, not to scale. But if I have a grid, each of which allows me to store the color of that pixel in the screen, you can imagine now using, let's just say 1-bit color. So here's that old monochrome screen from yesteryear. The grid, it just means you have rows and columns. And either I want to put a 1 or a 0 in each of these boxes. Well, how do you represent an image? Well, let me try something kind of arbitrary. How about 1, 1, 1, 1, 1, 1. No, not there. 1, 1, 1, 1, 1. This is not the scale, damn it. I'm just going to, well, OK. 1, 1, 1, 1, 1, 1. What did I draw? It was just a filled-in circle. It was supposed to be a smiley face, but then I realized I didn't leave enough room for the eyes or the nose. So this is a circle. This is how a computer would represent a circle. But it really is as simple as that. So if you think back to those green and black screens, all that was going on was the computer had a pattern of bits, but in this case it was 1 bit per cell in this grid of rows and columns. And if it were a 1, it should be green. And if it should be black, it should be 0, or vice versa. It doesn't matter so long as we're consistent. So now this is an image. An image is a sequence of pixels. A pixel is just a pattern of zeros and ones. Those zeros and ones are just 3 different numbers, and those numbers are respectively just patterns of bits. Notice the layering, and this too is going to be a theme of today or tomorrow. Lowest level, which we won't really come back to beyond today, is the bits, the zeros and ones. Now we're at this point in the story where we've forgotten about bits and letters and pixels. We're just talking about images. What comes next? Well, what's a video? How do you implement a video as an engineer? Grace?
Moving images. I mean, it's sequential images.
Yeah, it's just sequential images. So the phone book doesn't quite behave in the same way. But if you remember those little books from childhood where you flip the pages really fast, you would actually see like Mickey Mouse or whatever moving as though there were actually a video in your hands. But really all that's happening is you're seeing an artist's sequence of pictures where Mickey in one picture looks like this, then the next one he looks like this, until he's like waving at you. But that's just because it's 100 different pictures where in each one his hand is moving as though it's in a waving movement. And so that's all a video is. A video that you might double click or watch on YouTube or the like really is just a sequence of images, moving pictures, as they used to be called. Motion pictures are just pictures that move, that fly by the screen. We humans typically expect at least 24 frames or pictures per second, or TV commonly has 30 frames per second. Beyond that, we don't really notice the difference. Although, if any of you have a lot of smart TVs these days have like Auto Motion Plus or 60 hertz or 120 hertz. If you've ever noticed that like all of your TV shows on your nice new TV look like soap operas, like daytime soap operas, where like the movement is just sort of unnaturally smooth, and yet that is more natural because it's capturing more of the image. That's because you have this feature that manufacturers decided would be better, whereby even if a show or a movie has been shot 24 frames per second, they actually fill in the gaps. They interpolate what the scenes might have looked like for those split seconds between those frames, and the result is what looks more like a soap opera, which tends to be shot at like 30 frames per second, so they're just smoother, which is not necessarily the director or the photographer's intention. So that's all related there too. So if a video is just a sequence of pictures, well, to represent a circle, we need this many bits. If we want to represent a whole second in a movie, we might need 24 times this many bits, or 30 times this many bits if we want 24 pictures per second or 30 frames per second. And this is why videos are so damn large. Like there's so many individual pictures in them, those bits need to be stored. And that too is a bit of a white lie. In reality, there's fancy algorithms or processes for compressing things, so you don't need one true image per frame. But that's actually a perfect segue to the last of our ingredients, which is this one here. Algorithms. But where have we left things now? Started with bits, we went to numbers, we went to letters, we then went to colors or pixels, we then went to images, we then went to videos, and now we've pretty much abstracted away so far away we don't even need to care about the zeros and ones anymore. And indeed, when you walk out of here today and tomorrow, you shouldn't really care much about the zeros and ones that underlie any of your data because of this feature known as abstraction. And indeed, this is one of the powerful tools in a computer scientist toolkit. We're just playing with it verbally today. But indeed, when writing software, abstraction is actually a feature of programming languages that we'll see a little bit of tomorrow, whereby you don't need to know or care how something is implemented. You can think of a computer as just a black box that has certain functionality built in because other humans before you have abstracted away these lower level details. Or more casually, you can think of it as standing on the shoulders of people who came before you. Someone years ago figured out how to store zeros and ones. Someone after that figured out how to store letters and pixels. But thereafter, we humans can build on top of that work and implement things like pictures and movies and yet other file formats still. And so that general feature of abstraction or layering is actually a powerful ingredient when it comes to actually solving some problems. Yes.
Can I ask questions in between? Or
Yes, of course.
Okay.
JP.
One step I'd like to make, because I think you will stop on talking about that. So how does it work back to the bits? The bit we saw there on the screen, is it being used in several codes? So one bit is being used in several codes, like the color, the letter, the number, or is it being used once? And then how does the computer know to use that particular bit? That's for me difficult to understand.
Good question. The latter. A bit is only used one time. So if the picture that's on the screen right now is just the colorful version of this. So if this is a top-down view of a platter inside of your hard drive, which a platter is just like an old school record, and on this platter are whole bunches of bits that are either north-south or south-north. So they're not all ones. These are just actually, do I have any other colors? No other colors here. So there's all these little magnetic particles, much like the Wooly Willy photograph I pulled up earlier. So if you create a Microsoft Word file, the operating system, Windows or Mac OS or Linux or whatever else, decides, OK, that's a pretty medium-sized file. This shall be your resume.docx or some such file. If you then have an image like reunion.jpg from your family reunion, the operating system might decide, all right, that's actually a pretty big image. You took it at really high resolution. These bits shall be used for your reunion.jpg.
The number of bits, if you have a high definition screen, right? For every pixel you have, a huge number of bits.
Indeed.
And at times a few million.
Absolutely.
So the number of bits is insanely high.
It is. It is. So on our screen alone, so we can see this actually. In Mac OS, and Windows has an analog here. If I go to Display, I am currently in a resolution called 720p, which means 720 pixels top to bottom, and 1280, this is implicit, 1280 pixels across, which means on my Mac screen here alone, I have this many pixels, so 921,600, just on my screen alone.
But every pixel can have a different color.
Every pixel has a different color, and if my computer is in 24-bit color, that means I'm using this many bits just to represent what you are seeing on my screen right now. So this is 22 million bits are being used just to display what's on the screen. But that's OK, because let's consider this. So if that's bits, I didn't use this word formally before, but a byte, which is the unit of measure with which most humans speak, is just 8 bits. So to represent everything on my screen right now is actually just 2 million bytes. And how many bytes are in, say, a kilobyte? This is 2,700 kilobytes. And if I divide it again, if I divide it again by 1,024, it takes roughly 2.6 megabytes of information, 2.6 million bytes, to store the colors of everything you see on my screen here, whether it's black and white or perfectly colorful.
How does the know that that particular section has to be reserved?
Good question. So the latter piece of your question is answered by the operating system. One of the purposes in life of Mac OS or Windows is to manage the space on your hard drive. And essentially, all of the bytes on your hard drive, much like all of the bytes in RAM, the technology we discussed earlier, have addresses. So if you have a 4 terabyte hard drive, which is actually, let's call it a 4 gigabyte hard drive, which is actually super small these days, certainly. But if you can only store 4 gigabytes, you can think of each of the areas of this hard drive. If each of these squares represents a byte, you can think of this as being 0, 1, 2, 3, 4, 5, 6. You can imagine numbering all of the bytes of space on a hard drive. What an operating system has underneath the hood is a directory, many directories actually, that has at least 2 columns, the file and its location. So resume.doc might have an entry in this table, aka a directory, and it might be at location, looks like location 7. Whereas reunion.jpg, this is a little farther to the right, so I'm going to say that this is at location like 117. I made that one up. So your operating system literally has a table, not unlike what Microsoft Excel might do or Google Spreadsheets, that just maps file names to locations on disk. And in fact, this is a good opportunity to raise one of tomorrow's topics, privacy and security. What does it mean when you delete resume.doc. And better yet, suppose it's not resume, suppose it's like your financial information or passwords.docx. You decide, ooh, I probably don't want this anymore. I don't want someone seeing it, so you delete it. What does it mean in Mac OS or Windows when you drag a file to the trash can or the recycle bin? It just takes it out of the directory. And how can you recover the file still? Yeah, so it's in the trash can. So really, there's a separate table for what's in the trash can. But suppose you're smarter than that. You know that just dragging something to the trash can doesn't empty the trash, right? It's still actually there. So what happens when Mac OS or Windows users actually empty the trash can or recycle bin? That's all it does. When you delete a file, typically on a modern operating system, all you're doing is that. You're forgetting where the file is. But what have I not changed on the whiteboard? Right, I have not touched the magnetic particles on the hard drive, which is to say, if you remember programs like Norton Utilities or other such programs from yesteryear that claim to be able to undelete files, how do they do that? Well, they scour your hard drive looking for what looks like the remnants of files like resume.docx, and if it finds them, with high probability, it creates a new file with those same bits inside of them. So this is a side effect of computers remembering where things are by way of these directories. But deleting is usually just a matter of forgetting, not securely changing those zeros and ones to like random nonsense or all ones or all zeros. So this was a bit of a tangent from your question, but does that make sense as to how the computer is storing that information? In short, the computer has a little cheat sheet that remembers which bytes are used for which files. Yeah?
So over time, as you continue to use your computer, will the bytes sort of be reorganized and the files will eventually be deleted?
They will not so much get deleted, they will get overwritten or reused. Correct. You can't just delete bits. You can't remove, I mean, if you open the old school floppy disk and like rubbed it, you would move the magnetic particles off. That doesn't, of course, happen underneath the hood of your computer. But yes, you'll eventually overwrite files. And I'm oversimplifying. It turns out Reunion it wouldn't necessarily be all contiguous like this. Hard drives and SSDs get fragmented, where some files bits over here, over here, over here, over here. So really, you can think of this as being like a list. Well, some of the bytes are at 117, others start at 200, others start at 350, and so forth. So there's this whole notion of linking files together just so that you can consume the whole hard drive. However, if some of you had PCs years ago, you might have had something like Norton Utilities, one of whose features was to defragment a hard disk. And this is something tech people would sometimes recommend, that you should actually move around all the zeros and ones so that all your files are, in fact, next to each other for efficiency on the disk. The reality is these days disks are so fast that this is not a good use of time. So if people are still telling you to defragment your hard drive, they're living in the past for the most part. Let the hard drive do the thinking. Don't let the utilities that you pay for have to worry about it anymore. Used to be useful. Other questions? Yeah?
Related to the bits, is the 8-bit, 16-bit, is that the reason for the Excel sheet maximum size?
Yeah, so for years, Excel would only allow you to have 65,535 rows possible, after which you just had to upgrade and pay for Microsoft Access, a database program. That was because they were using 16-bit values. And I know this only because in graduate school, I was working with really large data sets, and it was just convenient to be able to load them into Excel sometimes. And I remember like swearing under my breath when I couldn't load my really big data set because Excel wouldn't support it. So they've since upgraded. They now use bigger values for their rows. Yeah, David.
We're talking about 32 bits as being large enough for the gigabyte RAMs now, and then there's 64 bits. But now machines have what's called the 32-bit registers or 64-bit registers, and it seems like they're putting them in blocks and making them faster. What's that terminology for, and why is it used?
Sure. So a register is really the smallest usable chunk of memory inside of a computer. Those registers are typically inside of the CPU itself. When we say Intel inside, that means that it's an Intel CPU, central processing unit. And the CPU is the device that at the end of the day does all of the thinking in the computer. It does all of the arithmetic. And indeed, we didn't go down to this level. It turns out that all of the operations we know on a computer really do boil down to addition and subtraction and multiplication and just moving memory around. It really is that low level. So that's what the CPU does. So when someone claims that a computer has a 32-bit register or 64-bit register, that just means that when the CPU understands operations like add or subtract or multiply, the value on the left and the value on the right are each 32 or each 64 bits. So the bigger the register, the bigger the math the computer can do all at once. So computers can still do math on really big numbers, on 33-bit values or 65-bit values, but they need to use multiple numbers or multiple sets of bits to represent bigger numbers. The bigger a byte a computer can take out of a problem, though, typically the better. So 64-bit registers or 64-bit CPU can generally do more work per unit of time than a 32-bit computer. So more is better. And we're kind of in the stage of life where 64-bit machines are all the rage, and most of us in this room, if not everyone, have 64-bit computers. And I don't know if it's available. Mac OS doesn't say it here. Does it say somewhere? If I poked around enough, let me try this. OK, here we go. So this is an esoteric command that most people would never execute, but I just asked my computer via this text-based interface for information about it. And the fact that it says x8664 here and here, that means this is a 64-bit computer. All Macs are this way. PCs, some 32-bit machines still exist, and the symptoms you would run into is if you try and install an new program on old hardware, you might not be able to. For instance, Windows 10 maybe only works on 64-bit machines. I'm not sure. I'd have to Google that. But newer software often no longer supports older hardware. So that's the only time you would really care these days. Felicia.
Like the comment in memory, like if the program is running in memory, that's a speed factor. If you're referencing that because
Can you be more specific?
let's say the program is like some of these new business intelligence tools like ClickView or Tableau, like it runs in memory, as if it's a selling feature that.
Can you elaborate on what those programs are supposed to do, and I can try to infer what they mean?
Intelligence, they're doing calculations, drawing graphs. For Tableau,
I'd have to look closer. It sounds like stupid marketing speak to me. Like, I think that is meaningless. Like, that's where computers store all of their data while being used. I'm probably doing them a slight disservice.
I use them, and basically it's a difference. It's an analytics tool that it's preloaded nightly. So rather than querying against a database, it's done as aggregation.
Okay.
And you're doing an analytics against the. It's like pre-aggregated, pre-analyzed data that you're exploring, but you're not hitting against the database.
OK, so that's a little more, that's a little more illuminating. The reality is, and we won't really talk about this later today, but databases tend to be relatively slow, but it's where you store data long term, much like for files get stored on a hard disk. But insofar as they're slow, if you do want to do a lot of real-time analysis, it's better to read all of the data from the database where it could be living in disk space, like physical disk space, into RAM. But even then, it's not necessarily the database. You can have databases that themselves exist entirely in memory or in RAM, not on disk. So that's probably what they're pointing to. And they're probably how they're justifying charging you more for the additional RAM that's requisite for that. So before I impugn some software I've never used. But it's also a little bit of marketing speak, it sounds. Like, I would hope it would be in memory. So, OK, other questions? All right, well, let's address the last of these ingredients, algorithms, and make this a little more concrete. We've talked, dare say, ad nauseum about inputs and outputs and how we might represent them and how we might abstract from the lowest level details to the highest level incarnations of them. But what's important when it comes to things like algorithms? Well, I promised that I would take out this, and this is a problem that most of us don't really have anymore, looking up someone's phone number in a device like this. These days, you take out your phone, but even the phone is just kind of the digital incarnation of this, right? Because on Android or Mac, on iOS, if you go to the Contacts app, everything is still sorted alphabetically. So even though what we're about to do is very physical, turns out that even digitally, the problem is the same. It's just implemented not with physical hands, but with software. So more on that in a bit. So this is a phone book. Let's assume it's all white pages, and let's assume I'm looking for someone like Mike Smith. If I want to look up Mike Smith in the phone book, I could open up the phone book, look on page 1, look down. I'm in the A section, so Mike's obviously not here, so I keep turning the page, turning the page, turning the page. So these are step-by-step instructions for solving this problem. I'm supposed to be looking at each page for Mike Smith until I find him. Is this algorithm, these step-by-step instructions, correct for finding Mike Smith? Yeah, if Mike is in here, I will find him, but what's the obvious objection? It's just slow, right? This is silly. So grade school, 2s. I can 2, 4, 6, 8. This algorithm is twice as fast. Twice as inaccurate because I'm not really doing 2 at a time. But if I did this accurately, it's twice as fast. Is it correct? Yes? I heard a yes. I heard a no. It's not precise. How so? Yeah, so it's buggy, so to speak. It has a potential mistake because what if Mike just happens to be sandwiched between 2 pages as I fly by? So is this irrecoverable, or can I fix this? Or do I have to go back to the 1 page at a time approach? What's a fix for this algorithm? If I'm flying through the phone book 2 pages at a time and I don't want to risk missing Mike altogether. Yeah. I know it's alphabetical, so maybe my heuristic is if I hit the T section, I get better double back at least 1 page because I've clearly gone past Mike. Or maybe he wasn't there, but I better go back 1 page at a time. So you might fly through the problem twice as fast, but you might have to double back a little. So overall, the net effect is certainly a faster algorithm, but it's not quite as simple as just 2 pages at a time. But none of us are going to do either of these algorithms. What's a typical human going to do 10 years ago? Or recently, I suppose. Look for the first letter. OK, but I don't know where the first letter is. 2/3 of the way through. All right, so here we are. And I didn't go quite far enough. I'm in the M section. So what do I do? What comes next? I start turning 1 page at a time? Yeah, so second letter, but I'm in the M section, so I'm still looking for Smith's, S, so yeah, flop over like this much. So it's kind of the same problem, right? A moment ago I was here. I went roughly 2/3 or halfway, and I ended up here. But now I know by process of elimination, Mike has got to be in this half of the phone book if he's in here, because he's an S, and this is the M page. So both literally and figuratively, we can tear this problem in half once until, oh, so close, almost recycled. So now we have fundamentally the same problem, but instead of it being like, 1,000 pages, now it's only 500 pages, but it's the same problem. How do I find Mike Smith? I don't want to devolve back to the original algorithm. I again want to go, let's say, roughly to the middle, keep it simple. And now, went a little too far. Now I'm in the T section. But again, I can tear the problem in half, going to a problem that's now 250 pages, throw that half of the problem away. Problem is still the same. And so what's sort of amazing about this approach is that the algorithm is not changing. The input is changing. The input's getting halved and halved and halved and halved. So the problem's getting smaller and smaller until eventually, if I repeat this process, I'm left theoretically with just 1 page on which Mike either is or isn't, and I can decide whether to call him or give up if he's not actually there. So if this did indeed have 1,000 pages, that first algorithm, 1 page at a time, how many steps might it have taken me to find Mike Smith? Or anyone for that matter. Like, what's the upper bound? In the worst case, how many times can I turn the page to look for someone who may or may not be there? 1,000, right? Maybe it's not Smith. It's like someone with the last name of Z. And so I only really know if I go all the way to the end, might be 1,000 pages. So that's something. How about, though, the second algorithm, 2 pages at a time? Yeah, it's like 500 or like 501, just in case I have to double back 1 page to see if someone was in between 2 pages. So that's good. That's like half as big. But what about if the phone book is 1,000 pages and I use that third approach where I use Grace's intuition of sort of splitting it, or if you will, dividing and conquering the problem again and again? How many steps does that take? 60, even fewer if it's 1,000, but that order of magnitude, a little more, 10 or so. Right? You can go from 1,000 to 500 to 250 to 125 to like 67-ish. We have to deal with rounding errors a little bit, but we get to 1 page much, much faster. So if we were to plot this, we can reuse this space here. If we were to plot the relationship among all of these numbers, let's consider where we're at. So we don't have to worry too much about numbers. Let's just worry about shapes. If this is an XY plot, and this is like the size of my problem that a computer scientist would usually describe as n. N is the number of pages, the size of the input, whatever your unit of measure is. And then this axis is time, number of seconds, number of page turns, however you want to count things up. The first algorithm has a very linear relationship, whereby if there's more pages in the phone book, it's going to take me more seconds. Or put another way, if Verizon or whoever the phone book person is doubles the number of pages, instead of it being 1,000 pages here and ending up here, if we have 2,000 pages, it's going to double the amount of time. This isn't quite to scale, but this would have intersected twice as high on the chart. Meanwhile, the second algorithm, where I go 2 pages at a time, still has a linear relationship, but it's faster, so it's a little lower. In other words, I'm going to call this on the order of n. This is computer science notation for on the order of, or the size of the problem. Whereas this one I'm going to call order of n over 2. And I'm cheating a little bit. We normally wouldn't say that it's over 2 even here. But the shape is fundamentally the same. It's still a straight line. But if there's 1,000 pages, my first algorithm might take 1,000 seconds. But my second algorithm is only going to take 500. And again, not quite to scale. Otherwise, this would be split perfectly. But that third algorithm is kind of an interesting beast, because the bigger the problem gets, the more pages in the phone book, the bigger my bytes automatically gets. The first 2 algorithms, I'm always taking a 1-page byte or a 2-page byte out of it. But the third algorithm is kind of impressive. It takes 500-page bytes, then a little smaller, but still 250-page bytes, then 125-page bytes, which is certainly bigger than 1 and 2. So what might the shape of that graph look like? Just a straight line, but much lower? It's more of a curve. And if you remember your logarithms, it's something that looks a little like this. It never gets perfectly flat. It's always increasing, but it increases ever so slowly over time. And you can appreciate this in the following way. So one, we already know that if you have 1,000 pages, this third algorithm was the fastest so far. But this algorithm is way more powerful and impressive when you think about even bigger inputs. Suppose that Verizon had a 4 billion page phone book. Promise we'll stick with these same numbers. So 4 billion page phone book. With that first algorithm, 1 page at a time, how many pages might I turn before concluding that someone's in or not in the phone book? 4 billion, right? That person might be at the very end, and I might have to turn all 4 billion pages. Second algorithm, 2 billion, because I'm going 2 pages at a time plus 1. So 2 billion and 1 in case I have to double back. That's faster. That's twice as fast. But how many times can you divide a 4 billion page phone book in half, in half, in half, until you're left with just 1 page? Only 32. And that's kind of amazing. You start with a 4 billion page problem, and those first 2 algorithms take 4 billion or 2 billion steps, give or take worst case. By contrast, this fairly intuitive thing that we've been doing for 20, 30, 40, 50 years is so much more powerful out of the box, because it only can be divided in half 32 times before you actually get to the page in question. And that's why this line is so low. Even as the problem gets massive, still not going to take you all that many steps. Conversely, if Verizon doubles the number of pages next year from 1,000 to 2,000, each of those first 2 algorithms takes twice as long, either 2,000 steps or a full 1,000 steps for a 2,000 page problem. By contrast, if Verizon doubles the size of the phone book from 1,000 to 2,000 pages, and previously it took 10 steps to find Mike Smith, how many steps does it take for Verizon, if Verizon doubles the phone book from 1,000 to 2,000 steps, we'll use the third algorithm? 11. And that's what's really powerful. And so indeed, one of the exciting takeaways of computer science is that even though it, by nature of the hardware devices with which we're surrounded, might seem very unfamiliar, if not a little intimidating, the ideas that engineers and specifically programmers bring to bear on problems are often not that dissimilar to intuition we've long had. It's just a matter of applying that same intuition to bigger and bigger problems. Like, we don't really have 4 billion page phone book problems necessarily, but Google certainly has a 4 billion page web page search problem, or trillions of pages these days, or financial transactions in other companies, or logs in some data analytics company. And so there's so many applications of big data, so to speak, where by getting the right algorithm, the right middle ingredient here, really, really, really has an impact on the performance. And in fact, your question of hardware, too, is sort of a different view of the problem. Rather than focus on the algorithms, they were focusing on the hardware. And simply having more RAM, presumably, with which to query the data means things can operate faster because of that trade-off between cost and speed and size of memory. So these ideas are recurring, and they really aren't that dissimilar. So there's one catch here. Unfortunately, computers only really understand what you tell them. They're fairly dumb devices. They only know what we've trained them to know. They can't just infer or fill in the blanks. They can only do literally what they've been told. And so a useful way of seeing that is the following. Might someone be comfy volunteering and coming up front here? You have to be comfortable appearing on video. and turn on the internet. But we're all, no dumb questions here. We're all friends. Just need someone to come look at what's on my screen without anyone else seeing. Or looking behind you. I forgot about that one. No one look behind. Need one volunteer who didn't look behind already. Just one volunteer. One volunteer. There's like a room full of 25 people. No one is volunteering. All right. Who wants extra lunch? Then okay, Grace, come on down. Thank you. All right, so Grace is going to come on down. And one honor system. No one look at that TV, because I'm not sure how to turn it off without physically unplugging it at the moment. And let me go ahead and do this. We're going to give everyone else in the room, if you don't mind helping out for just a moment, can you give everyone, or just pass those around on the left, and I'll pass this around on the right. Everyone just take one sheet of paper. All right, so, okay, there we go. So, Grace, if you'd like to come over here. Grace now is going to be, we'll say, the programmer, and everyone else in the room should be the computer, playing the role of computer, so much so that you're only allowed to do what you're told to do. You can't make assumptions, and so any abstractions that you might have come in the room with this morning can't necessarily be leveraged because you can't ask any questions or clarifications, but we're going to see just how well Grace can communicate or can program the room such that she's going to give you some instructions. You're going to do what she says with respect to your pencil or pen and the piece of paper, and we'll see if you can draw exactly what Grace sees before herself here. So if you could tell people how to draw this picture, and let me hide it in this folder. Okay. All right, execute.
I'm going to draw 4 shapes on a horizontal line. Don't draw a line. Horizontally in the middle third of your page, which should be landscape. The farthest left shape is a square that is about 1/3 the height of the page, and it's in the middle between the top and the bottom. Directly to the right of that, in the second quarter of the page from left to right, is a circle. Then there is a diagonal line in the third quarter of the page that is from approximately the bottom of the circle to the top of the circle, same height as the square and the circle, and then a triangle that is also approximately the same height as those shapes in the final right-hand quarter of the page.
All right, end scene, thank you. And now let me come around, and you're welcome to return. I'll come around to everyone else just so we can project some answers here. And so one of the takeaways here to set the stage for what we'll do tomorrow, especially when we translate computational thinking to programming, is just how much in the way of detail we humans take for granted, and how a programmer, an engineer, really has to think through details at the lowest level so that what appears on the screen ultimately, or what the software does, is actually what's intended, but is expressed in as clear as possible way. If I can steal some of these sheets. Okay, we don't need to grab all. Let me just grab a few from each side. Over here, thank you. Over here. Okay, very good, thank you, thank you. Sure, thank you. Okay, sorry, there we go. Okay, that's okay. Let me grab a couple from the other side. All right. Okay, may I reach here? Thank you. All right. Wonderful. So we have a nice variety of interpretations here, if you will. And so let's take a look at what some of them came out to be. So here we have this one here. All right, looks quite a few of you had something that looked like that. Indeed, here's another such drawing. And notice actually they differ only insofar as which way the line goes, if you can see. Then we had some other interpretations here. This one had it touching. So that's a little different, but a similar angle. This one I like to see. So definitely a little different. The line is going the right way, but is inside. This one was sort of an undo, perhaps over there. This one's cute in some way, okay, over here. And then this one, too, was a little different. So reasonable people will certainly disagree, is perhaps one of the takeaways here. What Grace was actually drawing was this. So it looks like the majority, just over a majority, did indeed get this right. But you can notice the sort of ambiguity sometimes. And she did take some liberties, certainly, like assuming that we all know what a square is, which is fine. But think about a square. What is a square? That's kind of an abstraction for a lower level implementation of what really is just 4 lines that are all connected and form right angles with each other. But no one would say, draw 4 lines each at a right angle and equidistant. And so we just say, draw a square. And so that is an example of an abstraction that's useful, because otherwise you get lost in the weeds, so to speak, when trying to communicate. But it does leave possible some ambiguities, as we saw. The line going from bottom left to top right was misinterpreted in a couple of places. The triangle could perhaps have been rotated. I'm not sure if you specified if the flat edge was on the bottom, though most people just seem to assume as much. But that was not terribly precise. And indeed, it's no coincidence, perhaps, that some of the earliest programming environments, if any of you have heard of Logo, for instance, were sort of graphical in nature. You might write textual commands, but all you could do is tell a turtle, in one version of the software's case, to go up, down, left, or right, and he or it could put down a marker or a paintbrush, essentially. And if you turned on the paintbrush, it could actually draw a line as it moved around the screen. And so in this way, you could imagine that Grace could have really kind of belabored the point here. And she could have said something like, OK, put the paper in landscape mode, lift up your pen, hold it over the left third of the page, touch pen to paper, move it down 2 inches, move it right 2 inches, move it up 2 inches, move it left 2 inches. And with maybe higher probability, we would have all been able to draw it perfectly the same. But we would lack then the sort of mental model for what it is we're doing. And so these abstractions both help, as in the case of draw a square, but might potentially hurt if you're just trying to communicate to a higher sort of form device. And so if you think about maybe some of our more modern technology, iPhones and Androids and things like Siri and Cortana and the like, you know, those are trying to be more human-like so that you could say, hey Siri, draw me a square. Whereas back in the day, or even in this room, we might need to be ever more precise as to what that actually means. Let's try just one other example, flipping the tables this time if we could. Whereby we need one more brave volunteer to join me up here. Everyone's really busy checking their mail now or something. OK, come on down. And we have Griff, come on down. All right, so Griff, the only rule here is you take the pen this time, face only this direction without looking at any of the 3 screens that are about to spoil what this is. And everyone else here is going to play the role of programmer, and we'll sort of round robin, take one instruction from each person, see if we can't learn a little something from the previous example as to precision while still making it possible for Griff to get this right. All right, so don't look anywhere other than straight ahead. All right, and we're going to give you this one here. All right, would someone in the audience, not Griff, who should only be looking straight ahead, like to propose how to begin? Yes, Owen.
Draw a circle up near the top of the board.
OK, someone else. Yes.
Draw a straight line from the bottom tip of the circle to almost the middle of the board.
Straight line to almost the middle of the board. Good. Someone.
I'm sorry.
Oh, little longer. Little longer.
To 3/4 of the board.
3/4 of the board. There we go. OK. Someone else. Someone else. Yeah, Dan.
From the end of that line, draw it down, angled slightly to the left, like say a 15-degree angle.
7 o'clock.
Yeah, thank you, towards 7 o'clock.
OK. 7 o'clock. Someone else.
Do an identical line from the top of the original line that you drew. So, yep, an identical line, also at that angle.
Nice. So a little copy paste there. What's next?
Draw another line from where you just ended back to close to the end of the straight line that's going down.
Seems the computer is able to ask some questions here, but okay. All right, almost there. What's last, or next to last? Anyone? Yeah, Dan again?
From the point on the circle where the second line goes out, draw that same angle, but going to the right. So the first line will go to about 5 o'clock, and then it'll be another angle from the point, the two lines intersecting with the circle from there. Put your pen there. And now draw a short line towards 5 o'clock. A little bit longer, keeping with, keep going there. And now from the end of that point, angle it a little bit to the right again towards, say, 4 o'clock. Yeah.
All right, almost there, and I forgot one piece, one more step. One step remains, pun sort of intended. Okay.
Now we're using the clock. I go about 2/3 of the way down the long line.
Okay.
Draw a line to, I guess, 4:30. It's half the distance of that big line.
Repeat.
Start there.
Start there.
Draw a line that's as long as half the length of that line toward 4:30.
Draw.
Without looking at your watch.
And? Just that?
Oh, and then another line from there till 5 o'clock, the same length.
All right. And Griff, what do you appear to have drawn?
Person walking.
Person walking. All right, how about a round of applause for Griff? Thank you. So, and most of us upon first glance would describe this as what? Draw a stick figure. And what's interesting about this is that by contrast, whereas the square and the circle and the triangle on the line all have perhaps a more obvious semantic meaning, draw a stick figure is probably not nearly precise enough for anyone to have recreated precisely this stick figure that I just so happened to find on Google Images. Right? There's enough sort of kinks in his legs and his arms at certain angles that much more precision was indeed necessary. And what's interesting too is that on a few occasions we were sort of struggling to orient Griff as to where he should go. And so there felt like there was this opportunity even to add some metadata to the picture, whereby maybe every time we had him put his pen down, we could say, define that point as A or B, or just some way of verbally back-referencing it later. And indeed, we'll see a little bit of this tomorrow with programming. It's actually quite useful to declare things like variables, placeholders, so that you can reset yourself to some known past position. And we were using far more words to sort of reorient Griff when had we simply put some breadcrumbs, defined some variables, so to speak, could we have jumped right back to that point.